I want to announce a couple of things. One is we're going to spend about 10 minutes talking about some things on the test, and specifically about the separate, integrate, the differential equations, and then the first page, the integration of the trig forms. And the main theme for that is going to be efficiency. So I was actually really pleased with how you guys did in general on the tests. At the same time, you can see that there ended up being a curve on the test, and that was not because you did poorly, so much as that the raw score reflected a lot of small details that needed to be under control. And so I want to talk a little bit about how to be more efficient with those details so that they don't mug you and consume all your time, because all of you felt rushed doing this. So we're going to do that. We're going to talk Taylor series, Taylor polynomials for today. And because of our schedule, we're not going to get to remainders really until tomorrow. So I'm going to update your homework, and we'll slow down the homework just a little bit. Just because I'm going to work some testing. Yeah. So there it is. Let's take a look at the test, and we want to consider, first of all, the front page. The part that I was pleased about was that all of you, or almost all of you, set up all of your integrations correctly. So I'm really happy about where you are with the applications of integration. The issue then is finding a good, efficient way to compute them. What we have is the region that is defined by y equals cosine x on the top and y equals sine x on the bottom, which is actually concave down, so let me draw that correctly. There we go. And it became clear to all of you that the intersection point is at x equals pi over 4. And so now the question is, the first question is, what is the area of this region R? And all of you set it up correctly as the integral from 0 to pi over 4 of top curve minus bottom curve. And we went through and did an antiderivative. Like so, from 0 to pi over 4, and then you evaluated. I think everybody got this right. So that what you end up with is root 2 minus 1 when it does settle. Notice that 2 over root 2 is the same as root 2. So that was fun. Then I asked you for the volume of the solid whose base is R and whose cross-sections perpendicular to the x-axis are squares. And so all of you set up volume is equal to the integral of area dx. Of course, our preliminary work is to take a cut perpendicular to the x-axis and see that the cross-section is going to have a side of top curve minus bottom curve. And so we have the integral from 0 to pi over 4 of cosine x minus sine x squared. Okay, now here's where we want to be smart about our integration. And the way to be smart is to use trigonometric identities. We can go ahead and square this. That makes a whole lot of sense. And that gives us cosine squared minus 2 sine x cosine x. Let me give myself some room here to work. I'll erase this portion of it because I think we've all got that down. And we'll move this fellow to center stage so that we can work on it. So we have cosine squared x minus 2 sine x cosine x plus sine squared x dx. And here's where, by being just a little bit clever, we can save ourselves a whole lot of effort. Please notice Pythagorean identity. cosine squared x plus sine squared x is just 1. So that there is no need to appeal to double angle identities here. And the second is the double angle identity for sine. 2 sine x cosine x is the same as sine 2x. So that with just a little bit of trig magic, my integrand cleans itself up really nicely. And so what I get now is going to be pi over 4 for the integral of 1 minus, plus 1/2 cosine 2x from 0 to pi over 4. And that gives me pi over 4 plus 1/2 of, let's see, it's going to be 0 minus 1. The cosine of pi over 2 minus the cosine of 0. And there's my volume. Much, much simpler than appealing to double angle identity, the double angle identities for cosine squared and sine squared. The same kind of thing happens when we get to the next question, which says find the volume of the solid that is generated when this is revolved about the x-axis, correct? And so we have volume is equal to pi integral of big R squared minus little r squared. And that's going to be pi times the integral from 0 to pi over 4 of curve minus axis squared minus curve minus axis squared. And again, we have a little bit of trig magic because cosine squared minus sine squared is cosine 2x. So that I get pi over 2 sine 2x from 0 to pi over 4, which is going to give me pi over 2, and we're done. Those affinities really are magical. And then finally, the region S is revolved about the y-axis. This was probably the most challenging. We revolve the region about the y-axis. And when we do, if I try to do this by disks, I can look ahead and see that there will be trouble. Because I'm going to end up having to do everything in terms of y, which means I'm going to have to solve for both the top curve and the bottom curve in terms of y, and I'm going to have to find out where they split, and so my volume ends up being something really nasty. It's the integral of arc sine squared, arc sine x, or arc sine y squared from 0 to 1 over root 2, and then the integral of arc cosine squared, etc. Now it happens. Or I can use shells. And if I use shells, then I take a cut parallel to the axis of revolution, dx, and now I can say that volume is equal to 2 pi integral of radius height dx. And the radius is going to be x, and the height is going to be top curve minus 1 from 0 to pi over 4. Now, interestingly, if it's pretty clear I want to use parts on this. Several people tried to split this up into 2 integrals, which is fine. There's nothing wrong with that, except that it's not very efficient. If I treat this as u and dv directly, then I get a not too hard integral to deal with. So I have u is x, dv is cosine x minus sine x, so v is sine x plus cosine x, and du is dx. And we end up with u times v less the integral of v du. All of that from 0 to pi over 4. that's going to be plus cosine x minus sine x from 0 to pi over 4. And that's a little bit of a pain, but it's not too bad. When x is pi over 4, we get pi over 4 times 1 over root 2 plus 1 over root 2 plus 1 over root 2 minus 1 over root 2. And when x is 0, this term disappears, so that I end up with this right here. And the dust settles, and it's a little yucky, but not too bad. So that was probably the most detailed reading of all of it. So the key point to pick up from all of that is how to do this efficiently, and the answer is set up the do not evaluate. You guys did fine with this. Any other questions on that page? Okay, let's look to the differential equation. Is this correct? xy times 1 minus 1?
2
Times 2 minus 1. And we're given that y of 0 is equal to 1. There was a lot of good work on this, but there were places where the details kind of fell through. And so again, we want to focus on how the details happen. We're going to separate variables, like so. And then we're going to integrate. And I found it a little bit easier to use an indefinite integral here. We'll do the easy side first, and we'll put our constant of integration right over there. And on this side, we're going to have to do partial fractions. I think all of you figured out to do partial fractions on this. Pretty sure that's the case. So off to the side here, we'll write like so. And for the fractions, and let's try y equals 0, and when we try y equals 0, we get a is 1/2, and let's try y equals 2, and when we try y equals 2, we get b equals 1/2 also. So that was this. Okay, and so now we carry out the integration, and for the first term we get natural log absolute value of y, and for the second term, don't forget your repair. The derivative of the inside is -1, or the derivative of the bottom is -1, so we end up with minus ln of absolute value 2 minus 1. I did have one person who got a plus on that, and that made life really hard. Happens to everybody. Happens to me a lot. Negative signs. Okay? So where from here? Where from here is we have to solve for y. This, just getting to this point got you 4 points out of 6. Now we need to solve for y as a function of x. And we also need a value for c. So the question is which one to do first. And I kind of like finding the c first, if I can. So let's do that. When we have x equals 0, then we have y equals 1. So that lo and behold, c is equal to 0. We like that. That's very good. And then the next thing is going to be to use log properties to combine here. But even before that, I noticed that I have common factors of 1/2. So let's clear those fractions, get them out of there, and get the ln of absolute value of y minus ln absolute value of 2 minus y is equal to x squared. And now we use log properties to combine. So that we have a single log on both sides. Raise e to both sides. And get this. So now we have our branch choice. Do I want to take the positive or the negative value of y over 2 minus y? Well, we did branch choice by considering the initial condition, and y is equal to 1, which gives me a positive value here when x is equal to 0, which is a positive value there. So that means that we're going to take the positive branch of our curve, just like that. Now, where from here? Where from here is we're looking for y, and so clearing the fractions seems like a good idea again. And now I can combine like terms. Everything with y on one side, everything without y on the other. And a little bit of factoring is my friend. And we're good. So the solving for y was tedious. Notice that fully half of the ink spilled on this question is just getting from my implicit answer to an explicit answer. And so that's a skill that you probably want to practice. Questions or thoughts? Also, make sure I added up your points right. If there's anything that looks fishy on your test, let me know. So you've got two choices, first V test or second V test. You can't do the first V test really, because you don't really know the signs of x and y to compute dy dx. There was one person who did a fairly sophisticated argument, and I accepted that. The easiest way to do it is really the second V test. If you take the second derivative, if you take the derivative of dy dx, then you'll get an expression that you can easily evaluate with x, y, and dy dx. And then you can use the second V test. That's the easiest way to go about it. Yes?
So, like, you can, as soon as you get your implicit answer, you can solve for C.
Yeah.
Okay. That was probably what made me struggle so much, is because I thought, like, I always tried to get it into y equals something and then solve for C. So I had C with me the whole way down.
Yeah. So if you think about it less in terms of a procedure, what are you allowed to do? And if you think of more about it in terms of counting the table with what you know is true, you know that this is true, right? And you also know that y is 1 when x is 0. So that tells you what C is, whether or not it ever allowed you to do that. See what I'm saying? What's the phrase? Nice guys may or may not finish last, but naughty boys and girls solve all problems. In other words, don't be afraid to break whatever rules you seem to think you have, as long as you're doing good math. Okay, let's close the chapter on that. Again, as a class, good job on the tests. I think they reflected a good knowledge of the material and a growing ability to handle more detail than you had previously tackled. We're going to spend the rest of our time talking today about Taylor polynomials and how to construct them. And so I want to go back to something that we've been doing for a long time, and that is our local linear approximation, aka tangent line. And you remember that if we had a slope and a point, then we could use that slope and a point to construct the equation for the tangent line, which was approximately equal to f of x for x close to c. we had a picture for this. We liked our picture. Here's our f, and here comes our tangent line right at C. And so for x's in the neighborhood of C, the tangent line and the curve are approximately the same value. And we even computed an error on that. We said the error was the absolute value of the difference between these two, and we were suitably impressed that the error was small when x was close to C. What we like to do is extend this idea so that we can create not just a linear approximation, but a polynomial approximation, so that we have some kind of polynomial curve that will estimate, maybe this would be a quadratic curve. It would come down and estimate f of x for x is close to C. Or maybe I could get a cubic curve going on in here, and maybe my cubic curve would come really close to f of x for x is close to C, something like that. That would be cool. And the only question is how to do that. So our goal is to construct a k-degree polynomial and we'll call that t sub k of x. T is for Taylor, who's really kind of pioneered this. K is the degree of the polynomial, and that t sub k of x is going to be a polynomial centered at x equals C, that is the best estimate of f of x for x close to C. That's a pretty simple goal. It's much easier to understand than it is to write. Did you guys all read the handout on centering, and did that make sense? Good. Good. Handout made sense.
That's exactly what I read it, and I was like, I understood everything that it said.
Cool. All right. Very good. We are on track. Okay, so the only question is, what is the word best estimate going to mean for us? And it turns out there's a lot of different possible answers for this question, but we're going to take one particular definition. Different takes on best estimate lead to different kinds of polynomials. And in the wider world, I'm not even going to go there, but in the wider world, different kinds of polynomials are useful for different kinds of questions. One take on it leads to the best fit polynomials that we use in science classes. We're not going to do that quite. Instead, we're going to use this definition of best estimate. Here is our best estimate condition. We're going to say that t of x is the best estimate of f of x if all of the derivatives up to k, the kth derivative, if all the derivatives of t, starting with the 0th derivative, which is the function itself, up through the kth derivative, agree with all the derivatives of f of x. We had already done this with our tangent line. Notice that the characteristic of our tangent line or local linear approximation, I'll come back down in just a moment, was that the function f of c at x equals c was exactly equal to L of c. check that out. Plug in L of C equals F of C equals F prime of C times C minus C is 0. And also, the derivative of F was equal to the derivative of L of C. That's how we construct it. The slope of the tangent line equal the slope of the curve right at C. This is exactly what we're going to require here. T of x is going to be the best estimate of F if all of the derivatives of T, let's insert a phrase here, from 0 to K, agree with all of the derivatives of f of x from 0 to k, and here it is, at x equals c. So the idea is that we're going to create a polynomial that right at the center c incorporates as much information about f as it possibly can. So not only is the point correct, that's f of c, not only is the slope correct, that's f prime of c, but the concavity will be correct also, f double prime of c. And whatever name you want to put to the third derivative will be correct, and fourth and fifth up through. So let's put this in official math language. We're saying that t of c equals f of c, t prime of c is equal to f prime of c, t double prime of c is equal to f double prime of c, and so on, up through the kth derivative at c. That's our best estimate condition. And the polynomial that is so constructed is called a Taylor polynomial. Now, let's actually take this idea and put it into practice. We're going to do 2 examples, maybe one if we run out of time. And then we're going to take the logic from those examples and wrap it up into a nice form. Okay, so here's the way things will present to us. Find a third degree polynomial centered at c equals 0 that is best estimate of f of x equals kx. Notice how it's presented. We have a degree and a center, and we have a function that we're trying to estimate. That's how the problem presents itself. Let's do this the long way. And we'll take that long way and try to turn it into a shorter way. The long way is that we're going to explicitly write out t3 of x. Notice that I put its center at 0 because I have x minus 0, powers of x minus 0 there. I have a third degree polynomial, and I have undetermined coefficients a0, a1, a2, a3. And so my only job is to find the right a0, a1, a2, a3 so that I have a Taylor or best estimate polynomial. And I can do that using the best estimate condition. What's cool is I can generate those coefficients one at a time just by requiring that the function, its derivative, second derivative, its third derivative have to agree with first, second, third, 0, 1, 2, 3 derivatives and leave the x at 0. And here's how it goes. Let's compute, first of all, t3 of 0. When we do, something lovely happens. What do I get for t3 of 0? Which a? I get a0, because all of the other terms drop out. And I require that t3 of 0 has to equal f of 0, which is 1. So, I have found my first coefficient. a0 will be 1. Now, we'll come back and do the first derivative. And the first derivative of t, term at a time, a0 is a constant, it drops out. a1x, the derivative is a1. a2x squared, the derivative is 2a2x. a3x cubed, the derivative is 3a3x squared. Whereas f prime of x is equal to e to the x. And now my best estimate condition is that the derivatives of these two have to agree at 0. So I compute here, and I compute here, and what do I get when I compute t3 prime of 0?
A1.
Just A1. Right. All of the other terms drop out. And since these two must be equal, then lo and behold, I have my second coefficient. A1 is equal to 1. Are we tracking so far? Okay. Well, the same process now happens for the second and the third derivatives. T3 double prime is going to be, now I go through and take a derivative again. This guy drops out. I get 2a2s. I'm going to write this in a funny way to emphasize the pattern. What I really get is 2 times 1 times a2. I did a power rule here, and I got 1 times x to the 0 power. So I'm going to write it like this so that you can see something. And over here, I get 3 times 2 times a3x. And in a shocking move, f prime of x is equal to e to the x. So that when I evaluate t double prime at 0, what do I get? Everybody. No. I get 2a2s, that's right. I get literally 2 times 1 times a2, which is 2a2. And f prime of 0 is equal to 1, and these two have to be equal so that a2 is 1/2. Yes, sir.
I know they're equal, but shouldn't that be f double prime of x technically?
Oh my goodness, yes. Thank you. I got lost. And last but not least, we're going to compute our third derivative. And when we compute our third derivative, we get 3 times 2 times 1 times a3. And again, I know the 1 would be invisible, but I'm looking for a pattern here. And when I compute the third derivative, which I will spell correctly this time, I get e to the x. And when I evaluate the third derivative at 0, I get 3 times 2 times 1a3, which is 6a3, which has to equal the third derivative at 0, so that a3 is equal to 1/6. What would happen if I tried a fourth derivative? If I were to try a fourth derivative, then my agreement stops, because the fourth derivative of f is still e to the x, but the fourth derivative of my polynomial is 0, and all subsequent derivatives are 0. So the Taylor polynomial can only estimate using information for the first 3 derivatives. Beyond that, the third degree polynomial's derivative, fourth derivative, and beyond will be 0. And that's why the polynomial is only an estimate of the function and not the function itself. Okay, well, let's put it all together. We have found our coefficients, 1, 1, 1/2, and 1/6, so that we can say that our t3 of x is equal to 1 plus 1x plus 1/2 x squared plus 1/6 of x cubed. And that's it. The procedure was not too hard. It was a little bit tedious, but it was not. But it seemed pretty straightforward. How do we check ourselves? There's two ways to check. One way to check, the formal way, is to make sure that our polynomial meets the best estimate criteria for each of its derivatives. So I would check that T3 of 0 is equal to f of 0, which is 1, check. I would check that T3 prime of 0, which is equal to 1 plus x plus 1 half x squared. When I evaluate at 0, I get f prime of 0, check. T3 double prime is equal to 1 plus x, and so that's correct. And T3 triple prime is equal to 1, and so that matches the derivative. So you can check it formally like that. The quick and dirty check is to graph the function and its polynomial on the same axis. So let's do that and see what happens. Wrong calculator. And we'll let y1 be our original function, e to the, and we'll let y2 be equal to our Taylor polynomial squared plus 1/6 x cubed. That's good. Graph it. Here comes e to the x, very familiar curve to us. And here comes the third degree Taylor polynomial. And would you look at that? For x's that are close to 0, my Taylor polynomial provides a very good estimate for e to the x. And then as I get out away from, and you can just visualize and see that the Taylor polynomial fits the curve better than a linear approximation would. So by incorporating additional information, I got a better estimate for my function. But then as x gets away from 0, my estimate gets bad. And so at some point, we're going to want to figure out how that, and that will be our remainder here. Okay? Well, given the time, the only thing left for us is to try to take some observations about the process and see what we can figure out. What I want you to observe here is that when we computed the third derivative at 0, the second derivative at 0, the first derivative at 0, and even the 0th derivative at 0, all of the terms except for the constant term zeroed out. So that I ended up with one coefficient only. And that one coefficient only was multiplied by something. And what it was multiplied by was all of the previous powers of x that had come before. So this a2 came from the term a2x squared. And when I took two derivatives, I got 2 from the first derivative times 1 from the second derivative. And then everything zeroed out. When I took a3 right here, I got a3x cubed 3 from the first derivative, 2 from the second derivative, 1 from the third derivative, and there it was. Well, it's not too hard to see that the pattern here is going to be this, that when you take n derivatives of x to the n, you get n factorial. And so the result that we have is a very nice result, and that is that when I take the nth derivative, here we go. When I take the nth derivative of a Taylor polynomial, I will be left with only one coefficient plus a bunch of terms in terms of x minus c. When I evaluated c, all those terms drop out except the constant term, which is going to be I evaluate the nth derivative of the Taylor polynomial at x equals c, what I'm going to get is n factorial times the coefficient a sub n. And if that has to equal the nth derivative at c, then I immediately have a formula for my Taylor coefficient, which is going to be that a sub n will be the nth derivative at c divided by n factorial. Now here, because of time, I presented this to you as a kind of intuitive plausibility proof. What I'm going to do is put out a short formal proof so that you can see it. This allows us to compute these Taylor coefficients more efficiently. So let me choose one example just to walk through. Find the second degree Taylor polynomial that estimates f of x equals root x at center x equals 1. So here I have a center and a degree, like so. I'm sorry, you need something?
Yeah.
And so I'm going to march through and use the theorem to generate the coefficients. And then I'll have the polynomial. And it goes pretty fast. We're going to have our function f of x, and we're going to need to compute its derivatives up to the second degree. So those are my derivatives right there. And now I'm going to compute those derivatives at the center, x equals 1. So f of 1 is root 1. F prime of 1 is equal to 1/2. And f double prime of 1 is equal to negative 1/4. And then finally, I'll compute my coefficients with the theorem. So that a sub 0 is equal to f of 1 over 0 factorial. 0 factorial is 1. Remember that strange definitional, of 0 factorial. A1 is equal to f prime of 1 over 1 factorial, which is going to be 1/2 over 1, or 1/2. And a sub 2 will be f double prime of 1 over 2 factorial, or negative 1 over 8. And this work right here efficiently generates my coefficients for the Taylor polynomial. I just have to put it together. And here it is. T2 of x equals a0 plus a1 times x minus 1 to the first power plus a2 times x minus 1 to the second power. Tomorrow, we will practice doing this.